right, so we're next going to talk about memory allocation in C++. Okay, so question sort of informally posed is what happens when you declare a variable? So let's say we've got two examples. So you've got some function, void, myfunc, and then you declare myInt. What happens when you do that? Or let's say you have some different function, maybe it has the same name. And instead of having an int, you have an int pointer, and you say my pointer is equal to a new int. What's happening underneath the hood? So in order to understand that, we need to understand how C++ manages variables. Okay, so if you want to talk about data layout, the first thing maybe we should introduce is primitive data. For instance, there are characters. Those are 8 bits long, or 1 byte. There are shorts. Those are integers that are 16 bits long, 2 bytes. Ints and floats both are 32 bits, 4 bytes. And doubles are 64 bits, or 8 bytes. So they take up twice the amount of memory as a single float. So they're double precision. So when you allocate a variable, you're carving out a piece of available memory, and then how much you carve out depends on how large it is, how many bytes it takes up. So let's say you've got this function you declare here. So you've got myfunc, and it allocates an integer myint, and initializes its value to 2, and then maybe an array of 4 integers, my4ints, and then you specify the values here are going to be 1, 2, 3, and 4. Then what happens is that somewhere in memory, which I'm going to represent through this talk as just this big cloud, there's going to be sort of this growing contiguous block of memory. And at the top of it, you're going to have myint that gets declared. And then beneath it, you'll have my4ints. And the values in here will be initialized just as they were in this function. So you can see that there was this span of memory here for the 4 integers, 1, 2, 3, 4, and then the myint 2 is there. And then they end up right next to each other. It's kind of the point that I wanted to show here. Classes are somewhat similar. But they're, say, arbitrarily composed. They group together data both conceptually, so you can think about, say, all of the data that would go on with a cat. So it's its name, its height, its fur color, and how much, how many eyes it has. Yes, but also in memory, they're going to be grouped together. So when you allocate an instance of a class, you physically bind together pieces of data. So let's say you've got some class here, my class, and then maybe it has in it some float, some int, and an array of maybe 4 characters. Then if you allocate an instance of this class, say in some function, as you're executing this function, it declares, I'm going to declare a new instance of my class, name it MC, and then put it on the stack. And so what happens here is that you carve out a piece of memory, and inside this piece of memory, that's going to correspond to MC. There's space for a float, an integer, and then an array of 4 characters. And what happened here, when you allocated this piece of this object, is that it called the default constructor. As you see that there was, so there was no parentheses. It's as if the parentheses were here and they were empty. So given no parameters into this constructor. So it calls the default constructor for this class, which does nothing to the data. And so these 3 data members are going to all have some value that's just representing whatever was in memory there the last time that piece of memory was used. So it's garbage, it's question marks. You don't really know what's there. You should never assume that what it's going to be is some meaningful or useful value, like 0. When memory is allocated the first time, who knows what used to be there? Okay, so how does it work if you have inheritance? Well, let's say you've got some base class, and there's a data member, the base class integer, And then you declare a new derived class. So you say class derived class, and you put a colon. And then you say this will inherit publicly from base class. And let's say that there's also a derived integer in this class. Then if you create an instance of your derived class somewhere in your code, then when this executes, the program is going to carve out a piece of memory for your variable DC, and it will have space for both pieces of data. It has a piece of data for the base class and a piece of data for the derived class.
And when you write a script and run it multiple times, does it carve the data out in the same place every time you run it?
So maybe you mean if you run a function multiple times as opposed to?
Yeah, anything that you write, that stores data. If you run it, I don't know, like if I run it this week and next week, will it be accessing the same points in the memory?
Yes. But so yes and no. Okay. So let's say you write a function and you call that function twice. Say you got another function and that calls it twice, your function. So function 1 is called by function 2 twice. So every time in both times that function 1 runs, it runs sort of with the same beginning location in memory where it will put its data. You're like just 2 slides ahead of me. So maybe I'll return to your, so yes, but if, say you enter the function from 2 different locations, then it might live in 2 different sections of memory. Maybe it'll be a little more clear in just a moment why that would be. Okay, so there are basically 2 places where memory gets placed, or where how it gets carved up. So there's the stack, which is where variables get allocated, say, inside of functions. The stack is a linear ordering of variables, and it sort of grows. Strangely, it grows downwards. But as you call functions, more variables get put onto the stack, and then as the functions exit, they get taken off of the stack. The stack is a very common data structure. It's useful for, it's very useful for say, having a representation of all the functions that have been called. You could imagine it being useful for, let's see. I'm going to come up with an example here, but not quickly enough. How about instead I just say it's very useful? You can visualize it conceptually as, say, a stack of trays for a cafeteria, where you're putting down, or maybe the person who's cleaning puts down a stack of trays, and then they get picked up in the reverse order in which they were put down. So the first tray to get picked up off the stack is going to be the last one that was put down on top. And the last tray to get picked up off the stack was the first one that was put down. So this is a LIFO data structure, last in, first out. You can talk about, so if the common operation for stacks is to pop, and the first variables that gets popped off the stack are the last ones that get allocated. And that's how it works when you're popping off variables in calling functions. The alternative to the stack is the heap. Heap is let's just say, a not intuitively ordered. You could think of it as disordered, but that's inaccurate. It's actually highly ordered, but it's not intuitive how it's ordered. It's a region of memory that's available to your program to put data into. When you call new, then you request space on the heap. And when you call delete, then you're returning memory to the heap to be used for future purposes. So 2 objects that are allocated, say, one after the other by your program, if the first object was declared with new and the second object was declared with new, they're both allocated on the heap. They're not necessarily next to each other on the heap in the way that the variables were next to each other in memory in the examples that I just showed you. Okay, so there's the stack of trays. Okay, so
Andrew, you should mention that the heap is RAM, right? So the heap is RAM and the stack is a different place, a cache.
No.
No.
Yeah, the stack so Jared was saying that the stack is RAM and the heap is someplace else, but
No,
well,
the heap is
Neither one was correct. So they're both RAM. Yeah. Yeah. Okay, so the stack, we're going to talk about this. Okay, so let's take some function, say my func, I'm going to declare in this function the integer 5 and the integer 7 and initialize them to the values 5 and 7. And then I'm going to call this other function within it called swap. And inside this function, I'm going to pass the two parameters 5 and 7 into it. So this function swap is going to take an integer reference A and an integer reference B. It's going to initialize this value temp to the value that's in A. It's going to assign the value A to the value that's in B, and then it's going to assign the value B to what's in temp. This is canonical swap. So let's see what happens when you execute this function. Okay, so this isn't animating, strangely. Okay, so maybe not the right animation order. First, when you enter my function, you allocate space on the stack for the variable 5, space for the variable 7. They're right next to each other. I've got to the left here the address in memory that each of these occupy. So this is kind of the label that the program's going to use 5, but it actually lives at a particular location. This is a way of writing hexadecimal numbers. So you just have a prefix here of OX. That just says what follows is hex. Hex is base 16 as opposed to usual numbers, which are base 10. And so since we only have 10 digits, we just go into the letters. So the first 6 letters of the alphabet become the next 16, or the numbers 11 through 16. So C here is just like the number 13. Okay, so 13008 is one hex location in memory. And then 4 bytes later, you'll have the next memory. And strangely, the stack grows downwards. It's just a peculiarity of how this was decided. Okay, so then we're going to call this function swap. So we're going to enter the swap and allocate a variable temp. So what happens is, first the compiler is going to put a whole bunch of data onto the stack for you. The compiler needs, the program as it's executing it needs this data so that once temp exits, you can actually get back to where you just were. This temp is going to finish doing its, swap is going to finish doing its thing, and then it needs to go back to my func. But swap is not written in such a way such that it knows exactly who's called it. It just knows that whoever called it has left information that it's going to use in order to get back to where it was. And so when functions exit, they use this little bit of data here on the stack to return to where they just were. There's like a top of stack pointer. There's a program counter that resets where the program is. And then I guess there's a convention about the contents of a few registers that always get put onto the stack. In any case, we call this the C calling convention. And there's data that's associated with it. And I'm just going to give it 3 lines, but I can't remember exactly how many pieces of data it requires. Anyways, so a little extra data gets put onto the stack here. In addition to that, you have the actual, these are called the formal parameters. When you declare a parameter as a function, you actually allocate space for that parameter on the stack as you call that function. And so A here is extra data that's required as an argument to swap. And then this is going to take its value from 5, because that's what I passed in as the actual parameters. So 5 has some address, and I pass the address in, and that gets written down as the contents of the variable A. So this reference here is holding a location in memory. It's actually a pointer, right? It's not treated by the C++ language as a pointer, at least syntactically. Right? You don't have to dereference it in order to use it. But when it gets written down, say, in memory, in machine code, is actually holding the contents of memory. It's a pointer. Okay, so this all happened before we even got to temp. So by the time we get to temp, we have memory allocated for the C calling convention data, the variables, the formal parameters A and B, which get put onto the stack, and then now we're going to initialize the value of temp to the value that's in A. So it's 5. So as we advance through this, the next thing that happens is that we assign the contents of B to the thing pointed to by A. So that's going to adjust the value up here to be 7 now. So now they're both 7, but fortunately we have a copy that we made of what was in A, and then we assign that copy of what was in A to what was pointed to by the reference B, which is going to be the variable 7. So now you've succeeded in swapping the contents of two variables with this function. You would have to dereference a pointer. These are they're internally the same thing. They're very, very slightly different, but they're internally the same thing for the sake of the machine. The machine knows that this is an address, but in the code, a reference doesn't need to be dereferenced. You don't need a star here because it's not a pointer to an integer. It's a reference to an integer. So references are these different things in terms of as you write code. There are a couple like safety things that you can't do with references that you can do with pointers. You can't change a reference after you've initialized it. A reference, once it gets initialized, never changes. You can change the thing it's pointing to. You just can't change where it points. Okay, so once this final assignment to temp completes, of temp to B completes, then the function exits, and this data is popped off the stack. And in order to say, figure out that you return to this part of the code, the data that was sort of sitting here in the C calling convention, that block of data helped restore execution to where you were when the function left, or when the function was executed. Okay, so how would recursion work? So you guys had a little bit of, yeah, Tina? Sure.
Why do you choose to say int temp and then a bracket instead of?
I think the actual, like under the hood, it's not going to make, oh yes, of course. The question was, why write int temp and then in parentheses a, as opposed to int temp equals a? It's just style. In this case, it looks kind of like a copy constructor. Like I'm going to, as if int were a class and I could initialize it using the value of another integer, then I can pass it in this way. I guess it also looks a little bit like a cast, which is something that you can do in C. You can just cast between different types. And you would do so by, say, declaring the thing that you're going to cast it into. So you could do, well, in any case. But what actually happens when you execute this code as opposed to just declaring it and initializing it in the same line, it's actually identical. I don't know if we're going to talk about this, but if you do the same thing with a variable, with a class, so if you had my class temp, and you said equals the instance MC, the instance of some class, it will actually invoke the copy constructor and not the assignment operator, which is a little funny, because it looks like you're doing an assignment operation, an assignment statement, as opposed to a copy construction. But, so yeah, it's just a style thing. There's really no substantive difference between declaration and assignment in the same line versus declaration and initialization in a copy constructor like syntax. Yeah, I don't think we have a coding convention on it.
Actually, I think the coding convention states that you should use the copy constructor with the parentheses to initialize things because it is using the copy constructor to do so, and it makes it a little more clear, although it's a loose recommendation.
Or classes that are not.
Yeah, so just to repeat into this microphone what Rocco just said, and the problem is that when we edit these videos later, we may lose this boom mic. So I'll just repeat questions that get asked and then also things that get shouted out at me from the audience. But Rocco just said that the coding convention for classes is that when you initialize them to use the copy constructor, since it actually is more suggestive of what's going to happen under the hood. Okay, so what does recursion look like? You guys had a Fibonacci example where you actually had to use recursion. So what happened when you actually wrote your recursive functions? Okay, so here's a countdown function, right? It's going to take as argument some integer x. It's going to print out x, and then if x is greater than 1, it's going to invoke itself with the value x minus 1. And then if it's not greater than 1, then it's going to yell blast off. Okay, so what is this program going to output? Three to one blast off. Okay, so how will it actually execute? So all right, so we're going to begin here in countdown 3. We'll call the function countdown with 3 here. So x, the formal parameter for countdown, gets initialized to 3. We put some data on the stack. So at this point, 3 is going to get output to standard out. And then we're going to invoke countdown again with x minus 1. And so this is going to put some calling convention data on the stack, and then also 2, right, for the formal value, the formal parameter x. This is going to continue because 2 is greater than 1 to a final call of countdown where x is now going to get the value of 1. So I now have 3 values of x on the stack in different locations in memory, but corresponding to 3 different invocations of countdown, and then the value that gets used here. All right, and then after we've gotten down to x equals 1, so this will stop. I'll print out blast off, and then I'll start popping data off the stack. So the first thing that gets popped off is the value of x equals 1 here, since this is the last function to get called. The next one to get popped off the stack is going to be the value of x when it's 2. And then the last one to get popped off is the value of 3. Okay, so what's funny about the stack is that you can corrupt it. You can totally hose yourself by changing the contents of the data that tells you how to get back to where you were. All right, so here's a stack corruption example. I've written this function corrupt. It's going to take a value, an integer val and an integer offset. It's going to initialize a pointer to the location in memory where offset lives. All right, offset is the formal parameter. It lives on the stack. So I'm going to initialize this pointer to point at offset, to point at this variable. And then I'm going to change the pointer by incrementing it by whatever value was in offset. All right, so this is looking at its location, and this is looking at its contents. And then I'm going to dereference pointer wherever it points now and add into it the value that's in val, whatever that is. So I'm changing some location in memory. This is a bad idea. And then I'll print out what's in pointer. Okay, so here's my function that I'm going to run. So I'll call from main, test corrupt. And I'm going to start it with I equals 0, and I'm going to increment I, and I'm going to call corrupt of 5. 5 will be val, and I will be the offset. Okay, so the first time I call it, I call corrupt 5, 0. So I get the value pointer, initialize it to offset. So here I put some C calling convention data. Here's val, which is 5. Here's offset of 0. And then here's the pointer that gets allocated on the stack. And I'm initializing it to the location of offset. So that's C1, F0. Then I'm going to increment it, increment pointer by offset, which is 0. So it just stays put. And then I'm going to change the contents of pointer by val. And so it becomes 5. I animated something else there that I didn't mean to. Sorry. Okay, the next iteration through this, I'm going to call corrupt again with 5 and 1. And so now I enter this function. I've put in some C calling convention data on the stack. Val is 5 again. Offset is now 1. And then pointer, once it gets initialized to the location of offset, is going to be C1F0. So it's going to point at offset. And the next thing I do is increment pointer by offset. So that's going to increment in step sizes of int. So int is a 4-byte thing, And so when you increment it by 1, then you increment it by 4 bytes. So it's going to go F0 to F4. Okay, it's kind of a funny thing about pointer arithmetic. And now I'm going to increment whatever is pointed to at this location in memory by val. And so that was 1F40 is going to become 10. All right. You ready? Now I'm going to call corrupt with a value of 2 for the offset. So put in the C calling convention data. I initialize the value of val to 5, offset to 2, and pointer to the location in memory where offset lives, so it's C1F0. I increment pointer by the offset, so now pointer is going to point at this location in memory, and I'm going to change it to be 5 more than it was before. And so now, when this function exits, someone's going to look here for the location in memory where you should return. Like so, there's the program counter gets put on the stack. That's the location in memory where the program lives, what you are currently executing. And so instead of returning to test corrupt, I'll jump to some other location in memory. Who knows where? And if you jump to some other location in memory and then start executing that code, you've just introduced a huge security hole, right? So some hacker figures out you've got this bad code in your program, and so they write to the location in memory where, they figure out how to put their code somewhere else in memory so that when this function gets popped off the stack, you return and start executing their code. This is called stack smashing. Sorry, this question? Yeah, so the question, yes, thank you, was why did it go to C1F8 if it was C1F0? And so the funny thing is that this is an integer pointer, and integers are 4 bytes. And so when you increment them, you increment in 4-byte steps. So you actually will step through 8 bytes in memory if you increment by 2. And so offset is 2, so I'm going to increment by 2. So it went F0 and then 2 bytes from, I'm sorry, 2 4-byte segments from there is F8. Okay, so the stack corruption takeaway. Pointers give you the freedom to do lots of really stupid things. So you should be very wary of pointing a pointer at the stack. It's totally legal to do so. It's just not a good idea. References, on the other hand, are much safer. You can't change where a reference points. And so you can't corrupt your stack if you use references. Under the hood, they are in fact pointers, or they're very, very close to pointers. They're basically addresses. It's in fact a little bit faster to dereference a reference than it is to dereference a pointer, because pointers are not safe in the way that references are. So the operating system has to do more checks to make sure you don't try to dereference a null pointer, for instance, when you're working with pointers. But with references, it's not an option. You can't have a null reference. You might ask, okay, so I've got 2 stack variables and I want to modify one of them, and so it's nice to just have a pointer so that the code beneath it can do its logic to point to one of those 2 stack variables. How would I go about initializing a reference for that? And it doesn't seem like it's possible. Well, you can, in fact, initialize a reference to point to one of 2 different things. And you can use what's called the ternary operator, which is this funny thing. It's got a question mark and then a colon, really. So let's say you want to initialize this reference, int reference myref. So you can initialize it within this parentheses here. So this is the Boolean expression that begins the ternary operator. So is integer 1 less than integer 2? Then if so, initialize myref to int 1. Otherwise, initialize it to int 2. And that will let you modify one of 2 pieces of data in an identical way with just a single block of code. You just start using myref instead of int 1 or int 2. And also just be especially wary of incrementing a pointer, because that's how you're going to get into trouble. Okay, the heap. So you allocate memory on the heap with new. You should have seen that in, I think, a couple of your assignments. And you deallocate memory off of the heap with delete. And as I said earlier, there's no sense when you allocate memory on the heap that, say, two pieces of data that get allocated there will be allocated next to each other. There's no guarantee for that. And so you won't have a scenario where if you walk off the end of an array on the heap, you necessarily corrupt the next thing that's say, adjacent to it in the program as opposed to being just adjacent to it in memory. It's much slower to allocate and deallocate memory on the heap than it is on the stack, but it's much more flexible. Okay, so I'm going to give you 3 examples about allocating an object on the heap, allocating an array on the heap, and allocating, say, a complicated linked list class. Okay, so an object allocated on the heap with new. All right, so I've got this class, my class, and it's got 2 pieces of data, my int and my float, and say its default constructor initializes the integer to 0 and the float, to 1. So in my program, I'm going to declare a pointer to my class and set its value to 0. And then using new, I'm going to allocate an instance of my class and then assign the pointer that's returned by the new, this call to new, to the MC pointer variable here. So here's MC pointer that was allocated, and then I say new, and what happens is that the heap is going to, or new is going to return to me a block of memory allocated on the heap, say in this location, CC18, and then this statement will assign it to MC pointer here. So you can think of there being like an arrow that points from MC pointer to this location here. That's how pointers are often thought of, is that they point, they indicate an area. But really what's going on is that there's just an address here. There's just a contents here in memory. So if you say, continue your execution, you pass the ellipse and you're done with MC pointer, then it's time to delete it, at which point you sort of return the memory to the heap. And so it becomes available for future calls to new. There won't be any in this particular program, but it's made available again. So that piece of memory is returned for future use. But one thing so this is kind of safe because you're just exiting the program here. There's really nothing more that could go wrong. But if you change your program, so instead of returning, you allocated a new object. So here's a new variable MC pointer 2. And you initialize it with new my class. So you're going to create yet another instance of my class and put it into MC pointer 2. Then to this point in time, it's entirely possible, and I'm going to say that it actually happened, that new will return the same piece of memory that it did last time. And so this block of memory now has been reinitialized. It's re-executed the constructor so that the values here are 0 and 1.0. And it's written down the value in memory into MC pointer 2 that is the same location that it was before, that it was for MC pointer. Right? And this is dangerous now because you have this variable still around and pointing at something that it ought not to be pointing to. Right? It shouldn't be able to point at somebody else's data, or rather, there's no reason to assume that they would necessarily point at the same object, and so it's kind of risky to have this reference to this location of memory to which bad things could be done, or the code could execute in ways that you don't expect. All right, and so if we were to go back to this example here of how you would clean this up, the canonical way of making sure that you don't have these dangling references is to set the value of any pointer to 0 once you've deleted it. And that effectively removes this arrow, so it's no longer pointing at this location of memory. Right, so this first example is an example of a dangling reference. Okay, I'll return to that idea in just a moment. All right, example 2, an array allocated on the stack with new and deallocated with delete, giving it these delete open and close square brackets. Yes?
What's the difference between setting equal to 0 and setting equal to null?
So Thomas asked, what's the difference between setting the value of the pointer equal to 0 versus null? Null is kind of a C thing, and 0 is a C++ thing. So it's mostly stylistic. Null, I think in C is a macro, and 0 is just 0. It's a literal. So I think, yeah, people just in C++ recommending it. I don't think that it has any functional difference. We just use 0 for everything in Rosetta++, or sorry, Rosetta 3 now. Okay, so, all right, so returning to my func here. So let's say I've got some array. I'm declaring that it's a pointer to integers. Arrays and pointers are actually the same thing. There's no functional difference between the two, at least when allocated in this way. So C++ is totally happy to let you treat a pointer as if it were an array, even if it's not an array. So that's something you should be mindful of. Okay, so let's say in the first line you declare the pointer to the array. The second line you allocate it with new, and then before you exit this function you say that you're going to delete this array. So how that works is that if we return to our cloud memory, here on the stack is int array, and when it gets declared, it's got garbage in it. Because remember, when you first allocate a variable and you haven't set it to anything, it just has whatever contents in memory it had before. And so at this point, it's FFFB. It's pointing off into a region of memory that you actually can't even get to, that the operating system will just shut your program down if you try to access. Okay, so instead, nothing bad happened between these two lines. You didn't try to do anything to int array, and so execution proceeds to here, where you allocate this array of n integers. So you have now a block of memory on the stack, contiguous block of memory, and the value, the location of memory where this block begins is going to be written down into the contents of the int array pointer. And so this points to the beginning of memory for this variable. I guess one other thing to point out is that when you allocate an array, you're also getting garbage, right? So this is just whatever was in that location in memory the last time something was run there. And so it's just who knows what. And then when you're done and you deallocate the array, then you say delete open close square brackets and then the name of the array, and it frees up this piece of memory again. All right, how about example 3? A list link of integers. How many people have implemented a linked list in a primitive language, or as opposed to just using an STL linked list? Okay, a smattering of hands. So this is how I had to do this when I was working in Pascal, or roughly how I learned to program a long time ago. So you have, say, a list class, and then you have a set of nodes. And the nodes are where you're going to store all of your data, but the list class is what you're going to interact with. And so this integer linked list, it should have a set of functionality that it should support. So you should be able to add a new link to the beginning of the list. You should be able to delete the first element in the list. You should be able to find a particular element of the list. You should be able to find and delete an element of a list. And then you should ask for the list to clean up after itself. So when it goes out of scope, when its destructor is invoked, it should go through and delete all of the memory that it's responsible for. Okay, so let's see how this would get implemented. All right, so I've got this int linked node. It has a pointer to the next node, and it's got some value that it stores. For its constructor, it's going to just initialize the value to whatever is given, and then it's going to set its next pointer to 0. And then it has a couple of accessors, so it'll return the value that it's holding with this val function. It'll return, I think there should be an underscore here, sorry for the confusion. If you ask for the next pointer, it will return that. It'll give you a copy of the pointer to the next. And then it has a couple setters, so you can set the val, or you can set the next pointer. So the class, the list class itself then is going to have a pointer to a node, and so that's going to be the head pointer. In its default constructor, it's going to initialize this pointer to null, to 0. And then these are the functions that we were talking about just on the last slide. So you should be able to push a new value into it. You should be able to pop a value off of the front of the stack. You should be able to ask if the list is empty. In this case, I've just given the implementation here. Just return whether or not the first pointer in the list is the null pointer. You should be able to get the first value, the value of the first element. You should be able to find a particular value, see whether it's in the list, and then you should be able to delete the first value. All right, so what would it look like to append a new element to the beginning of the list? So let's say this is the list that I have so far. So here's my list. The head pointer points at 3, 3's next pointer points at this 14, 14's next pointer points at 12, and 12's next pointer points at negative 23. So if I were to push the value 100 into this list, then I'd sort of I'd change the way memory looked so that there's this new node at 100, or with a value of 100, that's the first thing that's pointed to. So it's going to be the head pointer, and it's going to have its next pointer pointing at 3, at the previous head. Okay, so implementation-wise, so this would look something like, given some value, create a new element and initialize it with this value, then set the next pointer for this new element to the previous head pointer, and the head pointer to the new element. Does that make sense to everyone? Okay, how about this one? We're going to delete the first element of the list. So we're going to call this function list pop. And so if this is what the list looks like now, then afterwards it should look like this. So it should have a pointer to, the head pointer should now point at 3 as opposed to pointing at 100. Okay, so here's a way of possibly implementing it. Okay, so if head, that is if we're pointing at null, if head pointer is 0, then this will evaluate to false, and this won't, this next code won't be called, it won't evaluate. So if I have some pointer, then reset the head pointer to the next pointer. What do people think about this implementation?
You're just leaving it out there, and there's no way to leave it out.
Yeah. So the value, let's say in our previous case, you had the node with 100. You've just lost all reference to it. You've pointed the head pointer away from it, and there's nothing else that points to it. And so it's just hanging out in space, but it's not been returned to the heap, so you can never allocate anything in its space. So this is an example of leaking memory. So the more times this is called, the more things will get leaked, and the more memory your program will be using, but not productively. And eventually you'll run out of memory, and your program will crash. So in this case, you see the head pointer has been taken so that this is the next pointer of head, right? Points at 3, and so the head pointer now points at 3. So this part executed and produced that, but you haven't done anything with the value here. So you have to do something with that. All right, so what would the proper implementation of this be? Yeah, you could do that. So you assign head to something else, and then delete the pointer So, so shout that out to me. How does it work? So I'll give you the if. This be the int list node. Is that what it's called? Oh, it's not even on this one. Int. Yeah. So first you keep a copy of the thing that you're pointing at. Then you adjust head so it points to the. So this would be the thing that points at 100, and this would be the thing that points at 3, or that has the variable, the contents 3. All right, so you're going to adjust the head pointer, and then you're going to delete the thing that that used to be 100. Yeah. Okay, how about find? Oh yeah, so, yeah. Okay, so the next option is, or the next function to be implemented is find. So if we want to look for the node, or whether any node in this list has the value 12, we can call this function find and give it 12, and it should return true or false, indicating whether or not the list contains 12. Okay, so if the list looked like this, then we would start by, say, going to this node and looking to see if it's 12. And if not, we'd go to the next node and see if it's 12. And if not, go to the next node and see if it's 12. And if not, go to the next one. And then we'd find it, and so we should return true. All right, so an implementation of this might look like this. So here's the find function that the int linked list class would have. So this would be the val, and it would say, call this function of find node, giving the head pointer and then the value. And then this find node function, it would take a pointer and then the value that's being looked for, and say if this pointer is 0, then it's not in the list. We've gotten to the end of the list, and we should stop looking. So return false. But otherwise, then if the value at that node is equal to the value we're looking for, then return true. If neither of these hold, then we're at some node in the list that isn't null and it doesn't have the value we want, and so we just need to go to the next node. And so we'll call the function again. We'll recurse, giving the node up arrow next, and then the value. Okay, so if you wanted to delete the first integer in a list, what would this look like? Or the first instance of an integer in the list. So the first time we find 12, we're going to delete the node that has that value. So we start at 100, go to 3, we go to 14, we get to 12, and then we should delete that item and then fix up the list so that it's pointing in the right place. All right, so I'll give you a moment to read it. What do you think of this solution? Anybody have an opinion? Yeah. So, is it Shoria? Yeah, Shoria just said that the problem with this code is that after you execute it, say in our example with 12, then you won't be able to get to any of the other values in the list. We'll just sort of have left the list in a badly repaired state. So specifically, you'll execute this code. It'll find its way to 12 appropriately, but then once it, oops, what's going on? So it gets its way to 12, and then once there, it's going to return that that pointer to the list object, and the list is just going to call delete on it, right? And so there's sort of two bad things about the state that it's left the code in. First is that you can no longer get to negative 23, right? That's just been lost. There's no reference to the element with negative 23 anymore. And the second bad thing is that you haven't fixed what's going on with the node that has 14 in it, because it's pointing to a location in memory that's now been deleted. It's been returned. And so something else might get allocated there, and the next time we try to traverse this list, it's going to try and change what's in that location of memory, and then you're hosed. Okay, so this is an alternative here, where what you do is return the previous node. So we need not just node 12, but we need node 14. And so what you could do is ask for the previous node by calling this function. Let's just say it's going to return the previous node. And then we'll do the pointer arithmetic. We'll make sure that the next node, we'll write down who that is. And we'll get that out of the previous node. That's the one we're going to delete. And then we'll adjust the previous node so it points at the one after the one that we want to delete. So previous node up arrow next is going to be assigned to, it's going to be set to the value node arrow next. And then we're going to delete this node, the one with 12. Okay, so how would this work? So retrieve the previous node. So if the node that we're looking at is 0, then return 0. If the node val is the one that we're seeking for, return the previous. And and otherwise, keep going. So node will become previous, and node next will become node. Does that make sense? Does everybody like that solution? Okay, so it still has some problems, right? Because I didn't know what to do with the first instance. I just passed in the head pointer twice. And so if the element that you want to delete is, in fact, the head element, then this code, the previous slide's code, doesn't do anything to fix the head pointer. Okay, so you get to 100, and then you just delete 100, and you're done. Okay, so the improvement here is then to keep track of what you're looking at. So if the previous node, if the node that you find is actually the head node, then you need to set head to the new head. Oops, this has its own bug. Then you need to delete previous node. It shouldn't be delete head, or you're screwed. So you need to delete previous node. Otherwise, do what we just had on the previous slide. Okay, so pointers are kind of fun. I think that they're not, because STL list does so much, I don't think people just get to see very much like pointer manipulation, at least in comp sci classes anymore. Maybe I'm mistaken. I guess Sharon's seen them, so I'm proven wrong. But I don't know. I think they're kind of fun to think about and to work with, but they have their fair share of difficulties. And so there are really two big issues working with the heap. The first is a memory leak, where you can, if you aren't careful about making sure you return memory to the heap, you can actually just accumulate more and more cruft as your program executes until you've got no room for your program left, it's all cruft, and then the program crashes. Or you have the other problem of dangling references, where you keep a pointer to a location in memory even though you don't really have control over it. You've returned that piece of memory to the operating system to give back to you, or returned it to C++. And then if you're still pointing there, then you can do bad things to that location in memory and corrupt other pieces of data that you might not want to corrupt. Okay, so here's a function that leaks. I gave you one before, but here's another one. Okay, so this is an implementation of the Fibonacci sequence, where you allocate an array of size n using int, an int array, new int array of size n. You initialize it to v1, v2. Oh, so this is a variant of the Fibonacci function that starts at values v1, v2. In the one you implemented, you had v1 and v2 both equal to 1. So the first two values were just fixed. But you can have the Fibonacci series start at any arbitrary v1, v2. And it works exactly the way it would. And so if you have this code along here, you could allocate a new instance. I'm sorry, you would calculate the value for the ith instance of fibarray as just the sum of the previous two instances. And then the correct answer, is to return the n-1th position of this array. You will get the right answer out of this code. You will just use a lot of memory to do so. And so if you're repeatedly calculating the 57th Fibonacci number, then you have this problem that over time you're going to be allocating and leaking 57 bytes, or 57 times 4 bytes of memory. Eventually you'll run out. A dangling reference example would be, let's say I've got this mover, the Pack Rotamers mover, maybe by name inspired by Rosetta, Pack Rotamers mover, and the minimization mover, and they both have a score function pointer, sfxn, and the score function pointer is allocated on the stack, or sorry, allocated on the heap with new. So I say score function sfxn, so this is say inside main or some other function that I'm executing, and I initialize both the Pack Rotamers mover and the minimization mover to use the same score function, and then maybe I delete this score function, then I try to invoke the Pack Rotamers mover apply function with giving it a pose. So it's going to try and read this score function object. It's going to dereference the score function as it goes. And if the score function, has been freed, the program will most likely crash. If it doesn't crash, it's much worse than if it did. Okay, so the solution that we have in Rosetta in Rosetta 3 is to use smart pointers, and this takes care of both the dangling reference issue and the memory leak issue. So the solution that we have is that each object keeps a reference count, an extra piece of data that it has, and it's how many smart pointers point to it. And so every time a new smart pointer points at a particular object, that object increments its reference count. And every time a smart pointer points somewhere else other than at a particular object, that object decrements its reference count. And then once the reference count gets to 0, then the object, it deletes itself. Actually, I think the smart pointer will delete it. So it'll delete the object once the reference count goes to 0. No, reference count calls delete this. Never mind. Okay, so the way that works in our implementation is that we have all of our classes inherit publicly from this base class called reference count, and this lives in namespace utility pointer. So this colon here that says this is the scope in which this thing lives, and this is the namespace name. We'll go over namespaces a little bit more this evening. Okay, so here's this class. It has maybe one piece of data, myInt, and then maybe in its constructor it gets set to 4. And so when you allocate an instance of this object, there's some data that gets put on the stack. So there's a vtable, there's a the reference count, which is named count, and then there's myInt. I'm not going to talk about the vtable, but it's maybe nice to know that it's there. Count is this reference count object. That's the data member of the reference count class. And myInt is the private data of this class. So remember that the classes are composed of the data members of themselves and all of their parents. And so the my class has its own data, and then the data of its parents. So if I were to allocate on the heap an instance of this, so I could declare a new object. So this is a type def. I declare a new pointer, my class OP. So this is just a shorthand way of saying utility pointer, owning pointer, templated on my class. So my class op, my class OP, MC pointer equals new my class. So it's going to call the default constructor, and it's going to get initialized with the location in memory where the my class object got instantiated. And now count is going to be set equal to 1 because it's got one owning pointer that points at it. And myInt, again, will be initialized to 4. Okay, so the owning pointer class, it has its own versions of a constructor, a copy constructor, an assignment operator. All of these increment the reference count in the object that's being pointed at. The destructor decrements the reference count. So as owning pointers go out of scope, they get their destructors get invoked. And that will decrement the reference count on the object being pointed at. And then the object being pointed at, once its reference count goes to 0, it deletes itself. Okay, so one thing to note is that the assignment operator and also the assignment operator also decrements the reference count of the thing that it had been pointing to before it points at the new thing. Forget it. Okay. What was I going to say here? All right, so let's say I've got this instance of MC pointer, right? And I initialize it with a new instance here. So I set the pointer up like this, and then in the next line I say MC pointer equals 0. So I'm going to change the pointer so it no longer points at this location of memory. It's instead going to point at the null address, the 0 address, which is just the one location of memory you're not allowed to have anything, and so it's the thing you write down, you say you're pointing at if you're trying not to point at anything. And then when you set MC pointer to 0, so you write down the 0 here, then internally it's going to decrement the reference count in this object, and then the object will delete itself. It will return itself, or the space it required to the heap. There's one big limitation in using smart pointers, which is that if you get cycles in your ownership graph, then you can leak. So what would that look like? So let's say you've got a class that can hold a pointer to another, and I have two instances of this class, and I set their other pointer to be themselves. And then I decrement the reference, I set both of the smart pointers, MC1 and MC2, to 0. So pictorially, what's going on here is that you've got a piece of memory for MC1 and MC2, and then you have your two instances that you've created for each of those. And you've set the other pointer for each of them to the other. So this object now points at the one for MC1, and the MC1 object kind of points at MC2. And when you and once you've created this picture, then the reference count for this one is going to be 2 because it's got two smart pointers pointing at it, and this one is also going to be 2 since you've got two smart pointers pointing at it. And so when you set these to be 0, then they won't delete themselves because their total reference count, drops from 2 to 1, and this one drops from 2 to 1. but neither one has gotten to a value of 0 things pointing at it, and so it just persists in memory. So this is a leak. So when you're working with smart pointers, you have to think about who can point to what in an ownership fashion. We have a number of cases where there might be cycles, but we break them up with a special kind of pointer. So in the residue type set, for example, we have owning pointers from the residue type set to the residue type. And then we have back pointers from the residue type to get to the residue type set. So this is used, in the packer, where you say, okay, well, I've got an alanine in this position, and I want to consider all the other amino acids at this position that are built by the same residue type set. So if I'm in FA standard, then I get the FA standard residue type set. If I'm in centroid, then I get the centroid residue type set. And so I can build appropriate rotamers for all the other positions using, by starting with the residue type, with the alanine, and going back up to the residue type set that owns it. And if this back pointer were an owning pointer, then you would have cycles in your ownership graph. Access pointers, on the other hand, they're just these special pointers. They're basically raw pointers, but they don't increment or decrement the reference count that an object holds. And so the residue type doesn't own the residue type set. It simply points at it. Okay, so the other kind of funny thing about reference count is that in our implementation, the reference count lives with the object. And that's not the common way that reference counts are implemented. So for instance, the boost shared pointer is a smart pointer. And it keeps a separate object, it keeps a separate integer that is the reference count for each object. And so if you had an instance of my class, it doesn't need to derive from our utility pointer reference count class. It can just be declared. It's not deriving from anything. And when you allocate a new instance of this and you put it into a shared pointer, the shared pointer allocates a separate instance for the reference count for that object. And that solves this problem that right now you can only put into owning pointers objects that are pointed to, objects that derive from class reference count. So you can't have a standard list go into an owning pointer. And that's a bummer. We're actually trying to make the switch from our reference count implementation to this reference count implementation, just because boost shared pointers have a lot of really nice features that they come with. That is, other libraries using boost shared pointers provide some functionality it'd be nice to have. But anyways, this is something to be mindful of, is that now you sort of have two pieces of data that go along with the class, and if you try to separate the object from its reference count, it's possible. I mean, boost makes it difficult. Like, you really have to work to do it. But if you do that, then you could have two reference counts for the same object, and then who knows when that object is going to get destroyed. Like, it might get destroyed when it shouldn't be, and that's dangerous. Okay, so Amanda asked earlier what the purpose of the forward header was. So you have this forward declaration of this class. You say, I'm going to declare this thing called residue type. And you do this in the residue type.forward.hh file. And then what we also do by convention is add these type defs. Okay, so this, the reason that we add these type defs is because then they live in the right place. So I should probably tell you just a little bit about namespacing. So this says namespace core. That means I'm going to work with all things named in this particular space. And I'm going to give the name for this namespace, and that will be core. So now when I talk about anything that's inside of these brackets here and there, all lives within that namespace core. Namespace chemical is now just another declaration like namespace core. It's just one layer deeper. So this is now everything in this code block lives in namespace core chemical. And so I'm saying that there's a class residue type, and that's going to live in this namespace core chemical. And then there's some type defs, and these type defs also live in this namespace. So you can see here there's the utility pointer. That's the namespace where owning pointer lives. But the type def for residue type op, that lives in core chemical. So you can in your code, you can refer to core, : chemical, : residue type OP, and you don't have to type this whole thing, utility pointer, owning pointer, when you want to deal with residue type ops. So the two type defs that we recommend you have are ops and cops, apps and caps. So the ops are for owning pointers, the apps are for access pointers, and the C here is for constant. And so we'll talk about this in greater detail. I think Rebecca will talk about it on Wednesday, on how constantness works. Maybe I'm mistaken on the schedule, but the short version is that you can't change what's pointed to inside of a cop, but you can change what's pointed to inside of an op. Okay, so how am I doing on time, out of curiosity? What time is it?
2:40.
We started at, so this is right on target. Okay, so the last thing that I wanted to talk about was resource acquisition is initialization, RAII. And so this is, I guess it's common to a number of object-oriented programming languages. I think they do this in Java as well, where you rely on constructors and destructors to secure and to then later release resources that you're going to use in your program. And the nice thing is that when variables are popped off the stack, their destructors are called. That's what the language says has to happen, so compilers have to do that. And when exceptions are thrown, they unwind the stack. And as a consequence, they're going to pop off variables, and they're going to call destructors along the way. So that means if you have a function that has acquired some resource, and then it calls some other function, that other function, or maybe even itself, throws an exception, then your function won't start leaking resources. It won't keep reserving pieces of memory or mutexes, making them unavailable for other parts of your program to use. Okay, so some examples of this. And I guess the other thing that's really nice about them, not just for exceptions, but say if you have an early return from a function, you don't have to first go through and deallocate all of the pointers that you have in your function. It saves a lot of code. And it's just a lot easier to read code and to make sure that it's working correctly if resource deallocation happens automatically. All right, so examples of this are, say, the smart pointers that I just described, the owning pointers and not access pointers, but owning pointers, and the shared pointers, the boost versions of these. Standard vector uses this design construct. I won't call it a design pattern, but people often talk about RAII. Utility vector 1, which is basically a standard vector, also has this common property, so that when you allocate, say you allocate a vector 1 and you have 1,000 things in it, whenever that variable goes out of scope and it gets popped off the stack, then its destructor gets called and you return that valuable resource, that section of memory. Standard list does this, and often in multi-threaded environments, there are classes that you'll write to wrap mutexes. So you obtain the mutex when the class goes in scope, and then whatever causes that class to go out of scope, whatever causes to be popped off the stack, will release that mutex. That's really important if you're trying to figure out why your program is hung, or if you don't want to spend your time figuring out because you don't want it to hang in the first place. Okay, so here's an example of some function that is just going to behave badly. So here's this function, myfunc, and it's just going to throw 5. You can throw anything you want. Like exceptions don't have to be special exception classes. You can throw a string, you can throw a new instance of a class, you can throw 5. So this is just a silly function, but it's going to do something. All right, let's take a look at this function leaker. Right, so it's going to allocate 1,000,000 integers on the heap. Right, and it's going to call myfunc, and then before it exits, it's going to delete my array. And let's say I'm going to call this 1,000,000 times. And then, because I know that an exception is possible, I'll try to catch it. And if I catch an integer, then I'll say, oh, I caught an integer, print this out to the screen. And so if I call whoopsie from main, what happens? Uh-huh. So the exception gets thrown from myfunc, and so the program sort of exits up this way, right? So it's going to pop my array off the stack, but it's not going to execute anything down here. And it's going to bounce out to here. It's going to be caught. The exception is going to be caught. And then the program will continue. It'll go to the next iteration. And you'll do this, was that 1,000? 1,000 million? You do this quite a few times. And allocate, a meg each time, and then eventually you just run out of memory. And that's it, and your program exits. And that's a bummer. Okay, so the safe version of this is instead to allocate, say, a vector 1, a utility vector 1 of integers. And when you call myfunc, then it's going to throw an exception, and it's going to unwind the stack, and so it's going to deallocate, it's going to call the destructor on the utility vector 1. So each pass through whoopsie is going to print 5 over and over again, but it's not going to leak any memory as it does so. Okay, I think that's it. All right, are there any questions? Alex?
Is there ever any advantage to using an array rather than like a utility vector if it's a standard vector?
Okay, so the question was, are there any advantages of using an array over a standard vector or a utility vector 1? And the answer is very occasionally. So if you have a function that needs to allocate, say, 4 integers, and that every time you call that function, it's going to be 4 integers, then that array of 4 things can be allocated on the stack very efficiently. It can be put on the stack and then removed off of it without calling new or delete. If you have that in a tight loop, that can be have a very big performance impact, the difference between the new and delete version and the array allocation version. They're actually, so I've written my own, I think Boost has one. There are versions of array allocated stacks that you can write. So an array allocated stack, it's not going to leak memory because it's going to get popped off the stack regardless. So it's not going to solve, say, this problem, or rather, it wouldn't give you there wouldn't be a difference in regards to its behavior in throwing. But array allocated memories or raw arrays don't assert boundary conditions. So you can walk off the edge of an array on the stack and corrupt your stack. If you use a class, and the class has like methods to make sure that all of your, so every time you try to access a value, that you're accessing within the range of that array, then you can find bugs that would otherwise lead to stack corruption. And so if you look in the utility directory, there's a fixed size array1 class that is a stack allocated array, but that asserts boundary conditions.
Yep.